Bristol Community College, Mathematics with Dan Avedikian, Math 131, Elements of College Mathematics, Section 3.2, Problem 2. This is Section 3.2, Problem number 2. It says, consider the feasible region shown below. We have a big feasible region drawn here. Part A says, is it bounded or unbounded? This feasible region is unbounded. I did stop drawing it somewhere, but just because space is not unlimited, it does go forever. So this feasible region is unbounded. Unbounded. And then part B says, use the feasible region shown to minimize the object function z equals 4x plus 3y and state what point the minimum will occur at. So things that you would want to minimize typically are like cost, delivery time, things like that. And what the last one was maximize. What you want to maximize is usually profit, revenue, things like that. So minimize, the application to this would be to minimize some sort of a cost or delivery or setup time. So what we're going to do is set up one of those charts with 3 columns. The first column will be the corner points. The middle column, which I'll make a little bit wider, will be the object function. And for part B, that object function is z equals 4x plus 3y. And the rightmost column will be output. Now, this object function has 1, 2, 3, 4 corner points. So our chart will have to have 4 rows. So 1, 2, 3, and the bottom will be 4. And you can list the corner points in any order you like, as long as you don't miss any. The sensible order would just be to start at 0, 10, and then go right along the edge of the feasible region. So the first corner point I'll list will be 0, 10. The next one will be 2, 4. The next one will be 5, 2. And the last one will be 15, 0. Now, plug each one in and see what you get for an output. So the first one, 0, 10, I'm going to put in 0 for x and 10 for y in my object function. So that will give me z equals 4x becomes 4 times 0, and 3y is 3 times 10. 4 times 0 is 0. 3 times 10 is 30. And when you add those, 0 plus 30 gives you an output of 30. The next corner point, 2, 4, means x is 2, y is 4. So I'll put in a 2 for x and a 4 for y, and the object function for that corner point becomes z equals 4 times x is 4 times 2, and 3 times y becomes 3 times 4. 4 times 2 is 8. 3 times 4 is 12, and then 8 plus 12 more is 20. The next corner point is 5, 2, so x is 5 and y is 2. So when I put that 5, 2 into my object function, I get z equals 4 times x is 4 times 5, and 3 times y is 3 times 2. 4 times 5 is 20. 3 times 2 is 6, so 20 plus 6 more is 26. And finally, the last corner point of 15, 0. So x would be 15, y would be 0. When I put that in the object function, I get z equals 4 times x is 4 times 15, and 3 times y is 3 times 0. 4 times 15 is 60, and 3 times 0 is 0. So 60 plus 0 is 60. And now this question wants us to minimize. So keep in mind, we want the smallest output. Our choices for smallest output are 30, 20, 26, or 60. And the smallest one is certainly the 20. So the minimum is 20. And we have to state what point that minimum occurred at. So I'll put minimum 20 at the point. And as I look at the chart, the corner point that produced my 20 is 2, 4. So the answer to part B is The minimum output for my object function of z equals 4x plus 3y is an output of 20, and that minimum output occurs at the point 2, 4. So now part C is almost the same. So I'm just going to change a few things. I'm going to get rid of my answer for B. I'm going to change this to a C. And the only difference is the object function. So now part C is use the feasible region shown to minimize the object function is now z equals 6x plus y, and state what point the minimum will occur at. So it's the same process as B, except we're going to use a different object function. So I'm going to use the same feasible region, because that's what it says to do. I'm going to fill in the same chart with the same corner points, except my object function will be a little different. So I'm just going to erase the work that I did for the previous part. I'm going to change my object function. And I'll fill in this chart with the new object function for part C of 6x plus y. So the first corner point is 0, 10. So when I put that into my object function, I get z equals 6 times x is 6 times 0, plus y becomes plus 10. 6 times 0 is 0, and then 0 plus 10 is 10. So at the first corner point I try, I get an output of 10. The next corner point down is 2, 4. X is 2, y is 4. So if I put that in the object function, I get z equals 6 times x becomes 6 times 2, plus y becomes plus 4. 6 times 2 is 12, plus 4 is 12 plus 4 is 16. So at the second corner point I try, I get an output of 16. Now the next corner point down is 5, 2, x is 5, y is 2. So the object function now will be 6 times x is 6 times 5. Then plus y will be plus 2. So 6 times 5 is 30, and then 30 plus 2 is 32. And finally, 15, 0. So z equals 6 times x is 6 times 15, plus y is plus 0. Well, 6 times 15 is 90. And then 90 plus 0 is 90. So now we want to minimize the object function. And for part C, our possible answers are 10, 16, 32, or 90. And again, if we want to minimize the output, the minimum output we're getting is 10 with this object function of 6x plus y. So the answer to the minimum, I'll put minimum of 10. And again, we have to say which point gives us a 10. So minimum of 10 at the point so that output of 10 came from the point 0, 10. So that's the answer to part C. Part C is the minimum for the object function z equals 6x plus y for this feasible region is 10. And the point that produces the 10 is the point 0, 10. 0 for x and 10 for y. So now on to the next part, part D, which again is going to be almost the same. So instead of rewriting everything and redrawing the feasible region, just where it said C, I'm going to make it a D. I'm going to erase my answer from the previous part of the problem. And the only difference between part C and part D is the object function. So the object function for part D is z equals 4x plus 7y. So part D is use the feasible region shown to minimize the object function z equals 4x plus 7y and state what point the minimum will occur at. So to do that, again, I'm going to fill out the chart like we had for the previous parts. And I'm just going to change what the object function was. For part C, it was 6x plus y. But now that we're doing part D, the object function is z equals 4x plus 7y. And that'll change all the work for the rest of the chart. So let me erase. So the first corner point is 0, 10, which means x is 0 and y is 10. So my object function for my first corner point will be z equals 4 times x is 4 times 0, plus 7 times y is 7 times 10. 4 times 0 is 0. 7 times 10 is 70. So now 0 plus 70 is 70. So I get an output of 70 for the first corner point I try. The next corner point down is 2, 4. X is 2 and y is 4. So my object function will be z equals 4 times x is 4 times 2, plus 7 times y is 7 times 4. 4 times 2 is 8. 7 times 4 is 28. So 8 plus 28 is 36. That's the output at the second corner point that I try. The next corner point is 5, 2. When I put that into the object function, I'll get z equals 4 times x is 4 times 5, plus 7 times y is 7 times 2. 4 times 5 is 20. 7 times 2 is 14. 20 plus 14 more is 34. 34 is the output for the third corner point that I try. And finally, the last corner point is 15, 0. So x is 15 and y is 0. So z equals 4 times x is 4 times 15. And 7 times y is 7 times 0. 4 times 15 is 60. 7 times 0 is 0. 60 plus 0 is 60. And now again, we want the minimum output for this one. Our choices for minimum output are 70, 36, 34, or 60. Well, the smallest output is the 34. So for the answer, I will put minimum of 34, and then I'll put at the point So that 34 came from the corner point 5, 2. The minimum occurs at 5, 2 for this part. So the answer for part D, the minimum output is 34, and it occurs at the point 5, 2. Now the next part of this problem, part E, again, almost the same. So I'm just going to change just that object function and change this to part E. So I'll make that an E. I'll erase my answer from part D, the previous part, and I'm just going to change what the object function is, because that's the only difference. So for part E, the object function is 3x plus y. Z equals 3x plus y. So part E is use the feasible region shown, this one here, to minimize the object function z equals 3x plus y and state what point the minimum will occur at. So it's the same process. I'm going to go to that chart that I've been filling out, and it's going to have the same corner points because I'm using the same feasible region, but the object function will be different now. It will be different than the previous part. For part E that we're working on now, the object function is z equals 3x plus y. And again, technically you could think of it as plus 1y, but 3x plus y is how most people would write it. And I'll just make room for my new work. I'll just erase the work from the previous part. Put in my rows, put them back. And now we'll do the math and see which one gives us the minimum. The first corner point that I want to try is 0, 10. So x is 0 and y is 10. So z equals 3 times x becomes 3 times 0, plus y is plus 10. So 3 times 0 is 0, and 0 plus 10 is 10. The next corner point is 2, 4. So x is 2 and y is 4. And when I put that in the object function, I will get z equals 3 times x is 3 times 2, plus y is plus 4. So 3 times 2 is 6, and then 6 plus 4 more is 10. 6 plus 4 is 10. And the next corner point is 5, 2. So z equals 3 times x becomes 3 times 5, and then plus y is plus 2. So 3 times 5 is 15. 15 plus 2 more is 17. So the output at this corner point is 17. And finally, the last corner point of 15, 0. So z equals 3 times x will become 3 times 15. And then plus y is plus 0. So 3 times 15 is 45. And then 45 plus 0 more is 45. Now we have to state the minimum. And our choices for the minimum are 10, 10 again, 17, or 45. Well, the minimum output is 10. That part is easy. So I'll write minimum of 10. And now at the point, well, the thing is, I have to put at the points because there are 2 points that produce an output of 10. I get an output of 10 at the first corner point I tried, 0, 10. And also the point 2, 4. So I get that minimum at both the corner point 0, 10 and the corner point 2, 4. And in terms of stating the solution, that's enough. But in reality, you get that minimum output of 10 not only at both those corner points, but every one of the infinite points on the line that connects those 2 corner points. So you're also getting a 10 at any one of the points along the line that runs from 0, 10 to 2, 4. You don't need to say that in the solution, but that is what's happening. So we have one more part, part F. And that will end this problem. So for part F, let me just do the same type of thing. Instead of rewriting everything and redrawing the same graph that I had for the previous part, I'm just going to erase the E, make it an F, erase my solution from part E, just to make some room. Change my object function because that's the only difference in the question part E and the question part F. So for F, it's z equals 5x plus y. And to find the answer, I'm going to fill in the chart that I've been filling in. It's going to have the same corner points, but this middle column that lists my object function is going to have a different object function for part F. For part F, the object function is going to be z equals 5x plus y. And I'll erase my previous work to make room for my new work. And now I'm ready to answer part F. Part F asks you to use the feasible region shown to minimize the object function z equals 5x plus y and state what point the minimum will occur at. So I have my chart ready to go now. And I'm going to put the first corner point of 0, 10 into the object function z equals 5x plus y. And it will be z equals 5x becomes 5 times 0 plus y is plus 10. So 5 times 0 is 0. And then 0 plus 10 is 10. The output from the first corner point is 10. Now the next one is 2, 4. So z equals 5 times x is 5 times 2, and plus y is plus 4. 5 times 2 is 10, and 4 is 14. 10 plus 4 is 14. And the next corner point is 5, 2. So z equals 5 times x becomes 5 times 5, plus y is plus 2. 5 times 5 is 25, and then 25 plus 2 more is 27. And the last one is 15, 0. So the object function will be z equals 5 times x is 5 times 15, plus y is plus 0. So 5 times 15 is 75, and then you add 0. 75 plus 0 is 75. And now we want to state what the minimum of the object function is. So my choices for output are 10, 14, 27, or 75. Well, the smallest value is 10. So we can say minimum of 10. And then at the point, and my output of 10 came from the corner point 0, 10, from the corner point 0, 10. So as you can see, like problem number 1, you get different answers at different points of the feasible region. So it's not just what your feasible region is shaped like, but also which object function you're using with it. It will give you a different minimum and at different corner points. And that's it for number 2.